chapter 1. So chapter 1 should be a nice read for you as it reviews material on sets, mappings, and equivalence relations. Should be familiar to you from your previous study. Okay. Particular things to look at. Cartesian product of sets, which is Cartesian products of mappings. Okay. So sets and set algebra, intersections, unions, of course you're very familiar with. But looking here in the middle of page 6, we've got a Cartesian product. And this is going to be very important. Groups, of course, are sets. Group is a set with a certain operation on its elements. And one of the concepts in group theory is how to make more complicated groups from simple groups. And at the bottom, at the most fundamental level, what we'll be doing is taking groups and forming products of them using this Cartesian product structure. So if you have two sets A and B, two non-empty sets A and B, you can immediately form a more sophisticated set by taking their Cartesian product. And the Cartesian product, to remind you, is the set of all ordered pairs. Okay. So the set capital A has got a load of elements little a floating around in it. Set capital B has got a load of little b's floating around in it. But the Cartesian product of them, named after Descartes, of course, is the set of all ordered pairs. So an element of the Cartesian product is an ordered pair of elements, typically written, which we normally write as brackets, and then the ordered list within the brackets. And the first element must come from the set A, the second element must come from the set B. The Cartesian product is the set of all of those. How many things are in the Cartesian product?
In that particular one?
Well, that's a general one.
Could it be infinite?
Could be.
Could be empty sets as well.
Could be. What kind of answer am I expecting from that question? Obviously, it could be anything.
Related to the size of the initial set.
Yeah. So what's the size of the Cartesian product of A times B? And as Laura said, we expect the answer to be depending on A and depending on B. Mm-hmm. And it depends on it in a very appropriate way. Mm-hmm. That's another, because it's only 7, I'm going to be going around. Jordan's first.
Yeah, I'll leave now.
This course is easy. It's so easy. The answer is literally staring you in the face. So how many choices are there for the first element?
One. Well, for the first element in that bracket, 2.
Yeah. Well.
Or how many things are in A?
Yeah, you see the possibilities for the first entry in an ordered pair. Is anything from A.
Yeah.
How many different things might you see in that first bracket? However many things there are
in the bracket, yeah.
And how many choices in B? For the second entry?
As many as there.
As many as there are in B.
Yeah.
So if you got one set of choices combined with another set of choices, you've got 4 t-shirts and 5 trousers, how many different outfits can you form?
20.
4 by 5. The number of different choices here. Each one of those can be paired with whatever choice now. 3 choices. 4 times 5. Exactly the same here. So this is what I said, staring in the face. It's just 8. The size of A multiplied by the size of B.
8 times 2.
8 times 2. Okay? Or strictly speaking, we would write the order of A, so the modulus signs around it. The order of A times the order. Okay.
Modulus signs.
Good.
Yeah.
So that's the Cartesian product.
Just double checking.
We'll do some exercises with that in a moment. So if you look at the reading notes, also the things about maps and terminology associated to mappings. Okay. So we'll talk about functions from sets to other sets. Functions can be injective, surjective. Remember all that terminology, 1-to-1 and onto.
That's like first year, isn't it?
It is first year, yeah.
Yay.
It's third year once again.
I don't remember what I did yesterday. Yeah.
Theorem 1.5 brings together some good facts about injective and surjective and so on.
Oh, 1.15.
Yeah. So I'll just remind you that so injective.
Mm.
An injective, so if you've got a function f from set x to set y, f is injective. This means that for every pair of elements x1 and x2 from x, if f of x1 is equal to f of x2, that implies that x1 is equal to x2. So if your function takes the same value on two potentially different arguments, x1 and x2, the only way that can happen is if, in fact, x1 is equal to x2. So classic non-injective behavior is if you've got your domain here, x, and codomain, remember that's the terminology we use attached to functions, the domain and codomain of the function. So non-injective behavior is where you would have two distinct elements here, x1 and x2. So x1 is not the same as x2, but nevertheless, they both go under the mapping f to, say, this little y, where y is the value taken by f at x1, which is the same as the value taken by f at x2. So that's non-injective behavior. So a non-injective function is one that collapses two or more elements down onto the one image element. In a way, you're losing information, because you can't use this element y to represent, it's not going to represent the elements in the set x very well, because it kind of has to represent two different elements. So an associated concept is that so that's commonly called one-to-one. Yeah. And this is non-injective because it's 2-to-1 at least. Maybe it's even worse than that if you look at the other values of that function. Surjective, which is the onto terminology. Function f x to y is surjective. This means that for everything in the codomain, for everything in the second set y, there exists something in the first set that the function sends to y. So everything in your codomain over here has something from x mapping into it. It's a surjective function. Okay. So non-surjective behavior, or a function that's non-surjective, would look something like this. You'd have a bunch of elements here in the codomain, and some of them may have arrows, mapping arrows coming into them from the set x. But if there's at least one element for which there are no mapping arrows arriving, if there's an element for which there isn't a mapping arrows coming into it, then that's non-surjective, because that breaks this condition. Because this condition says for every little y in the set y, so for everything over here, there is something in the domain such that f of x equals y. So there will be something that's mapped across to it. Of course, the main piece of work I'm going to leave you with after today and for the following couple of days is to read through chapters 1 and 2. That's the you should see that's your very first instruction for everything we do is to give the chapters a good reading through. There is also introductory material there on equivalence relations, which you would have done in your decision maths unit in your first year. Perhaps with Jan, did he take you for the decision maths?
First year it was mandatory.
Yeah, but was it Jan?
Oh yeah, it was Jan and Philip, wasn't it?
Yeah.
Been doing
So
a
they
lot
would
for
have
3 years now.
They would have talked to you about equivalence relations and that. When we encounter them and when we need them, we will kind of introduce the terminology.
You would have seen that.
You should read through that as well. So let's dive in and tackle an actual question. So what about on the chapter 1 exercises there, you've seen the problem workshop session. Looking at questions 11, 17, 19, 25, 28. Okay, and we by no means do
Chapter 1.
all of these. And the end of chapter 1. So this is pages 14, and 15.
11.
Yes, let's have a look at. These are just some of the ones I recommend. So let's have a look at question 11.
Now when you read union, the one that looks like a union,
Yeah.
the N one is like and.
Yeah.
Right.
Intersect.
Intersect.
That's what we must do.
Really?
This is the only thing my foundation failed.
Page 14, question 11. So we're asked to prove a set equation. Prove A union B, Cartesian product with C, is equal to Cartesian product of A with C, union Cartesian product of A with, B with C. How might you describe that result, that equation? Alan is a central algebraic word, or a word that we often use in algebra. What's going on? I mean, this is you want to develop a taste, being able to digest things like this, not just see it as some kind of random formula, but related to other things that you know about. Sorry? Commutative. No. So commutative says your x times y or x plus y is equal to y times x. That's saying commutative if it doesn't matter which order you take the arguments to the operation. So here we're saying first do the union of A and B, and then take the Cartesian product with C. These are sets. Whereas the right hand says, well, first take the Cartesian product of A with C, then the Cartesian product of B with C, and then perform the union of them.
Expansion.
Yeah, something like an expansion. There's a technical word beginning with D we used for that.
It's on that massive list of
Yeah,
qualities.
Distributive.
distributive.
Ah.
That's a technical term. So what this says is that the operation of Cartesian product distributes over the union. Yeah, so you take your C here, and you give it to A, and you give it to B, distributes across it, and you're then taking the union of the results of the individual Cartesian products. So taking your Cartesian product with the union is the same as taking the union of the Cartesian product.
Yeah.
Okay, good. Okay, what kind of an argument? Okay, it looks reasonable, doesn't it? It follows the same pattern, for instance, as something like, 2 plus 3 multiplied by 4. If you want to, you can evaluate that as doing 2 by 4 first, and then doing 3 by 4, and then adding the results. That's addition. That's multiplication distributing over addition.
Mm-hmm.
Yeah. So it certainly looks plausible. It follows a pattern, well-known algebraic pattern, but it isn't addition and multiplication. It's union and Cartesian product of sets. So we should just assume that's true. So what kind of an argument is it looking for? Well, it's looking for some kind of an argument that relies on just the basic definitions of what union is and what Cartesian product is. And in particular, it's an equation saying that this set on the left is equal to this set on the right. Yeah. So a common approach, how do you show that one set is equal to another set? Well, sets are nothing but containers for their elements. So the identity of a set is completely determined by its elements. That's all a set is. It's just a bunch of elements. So to show that this set is equal to that set, what you do is you show it on the element level. So you take a general element from the left-hand side and you prove that it's also in the other set. That would prove that the left-hand side is a subset of the right-hand side. If something is in the left-hand side, it has to be in the right-hand side. Then you prove the inclusion the other way. So you take a general element from the right-hand side and prove it's in the left-hand side. after you've done those two directions, maybe you can do them in one fell swoop, or maybe you have to prove them separately. Then you'll have shown that the two sets have exactly the same elements. So in other words, they are the same set. Because a set is nothing but its elements. Okay. So that's the way we do it. So we would say let X be an element of the left-hand side. And just as in number theory last time, a common approach, or common tactic you can use for proofs is this bridging the gap kind of approach. Okay? You all remember this from last time. So we know the conclusion we want down here. We want the conclusion that X is an element of the set on the right-hand side. A cross C union B cross C. Yeah, that's what we want. So we just have to get from here to there using the definitions of the various ingredients. Now the top level thing, the top level operation that's taking place here, well, this union is taking place inside the brackets. That's kind of invisible to us a little bit. What we're seeing here is a Cartesian product of two sets. So this means our X must be equal to, let's just call it a U and a V, where U is an element of A union B, and V is an element of C. Yeah? That's what it is for something to be an element of the Cartesian product. Yeah? So all we're doing there is just using the definition of Cartesian product. Yeah? Well, and with an eye on, I mean, where to go next? Well, with an eye on where to go here, see, if we walk one step backwards from the conclusion, how would you conclude that X is in the union? What stage do you have to arrive at right before you can make that conclusion?
That there was elements of X in both. So that you could sort of collectively put it together.
You're on the right lines. X is an individual element. And this last line says X is present in the union of this set and that set. So what's the very previous thing you need to know about X?
That U and V are in then. Because then obviously if you knowing that U and V is collectively in X, in the step beforehand, if you knew that U and V existed, it is just X.
Yeah. Or maybe without bringing in the U and V into it. So like if, okay, for the sake of simplicity, there's two universities in Manchester, MMU and UOM. So what has to be true if I point at someone and say they're a student in Manchester, in the city of Manchester? Yeah, one of them or the other. It has to be true that they either come to MMU or they go to UOM. Yeah. So if X is to be in the union of these two sets, that's it. It must be either in this one or in that one. Yeah.
So
you were along those lines. So X is in A cross C or X is in B cross C. That Cartesian. The reason I stepped it back there is to kind of give us a bit of a hint about where to go with this. Because try and bring that logical OR in. Of course, the logical OR up here is in the union statement. Okay? Something is in the union if it's in this one or in that one. So this is saying that X is equal to UV, either because X is in A and V is in C, or, so that's one statement, or it's the case that the U is in B and the V is in C. And the V is always in C. The U is in the union of A and B, so it either means it's in A or it's in B. Yeah. It could be in both, could certainly satisfy both. Remember, OR is not exclusive. It could be in both. Well, That's more or less it, yeah? Because you've got X as U and V. I mean, if U is in A and V is in C, that means you're looking at an element that's in the Cartesian product A cross C, isn't it? Yeah. You've got an ordered pair. First thing's in A, excuse me, the second thing's in C. Or if it's the second case, you're still looking at an ordered pair. The first thing is in B, the second thing is in C. So that's exactly an element of B cross C. Yeah. So actually, that extra implication sign is a bit redundant there. We do now have that this implies this. Okay? The justification here was the definition of union. And the justification for this step here, this justification is the definition of, well, you're back to the definition of Cartesian product, definitions of A cross C and B cross C. We're just reinterpreting this OR statement. This is saying X is in A cross C. And this one is saying X is in B cross C. So that proves that everything in the left-hand side is in the right-hand side. So the left-hand side is a subset of the right-hand side. Okay. So that's only half. That's only half the argument. We then have to do the second half. We have to take something from the right-hand side and prove that it's in the left-hand side. So Calvin, do that in 2 seconds.
2 seconds.
I'm a fair man. I won't give you a question that's unfair. So why is it fair to ask him to do it in 2 seconds?
Because it just worked the opposite direction.
Yeah, it just works the opposite direction. Okay. Each of these implications, when you think about it and look at it closely, they're actually equivalences. So not only does this first thing imply this, actually it goes the other way as well. Because all we've been doing is just reinterpreting the definitions. So yeah, good. Do that in 2 seconds by just sticking the other direction of arrow on it. So actually that's equivalent to this statement. This statement is equivalent to this one up here. That statement is equivalent to this one, and this one is equivalent to the one before it as well. So notice, so when I first wrote it down, there were implications, but in red, these implications from top to bottom are actually equivalences. I'm working my way through it. Don't think I'll get you over my questions. Not this class, and the next one.
Confidence. Can I read?
But notice these implications are actually equivalences.
Equivalences.
So we can go the other way. Okay. So that proves the result. Everything in the union of the Cartesian products is in Cartesian product of a union B and C. Okay. I think we've taken our first few tentative steps into the unit. I'm going to see you again tomorrow after morning.
Is it
noon?
1?
Could be 1.
No, that's the project meeting.
Probably
3 o'clock, I think.
It's 3 o'clock, okay?
Or is it 3?
Yeah.
If you can,
3, oh yeah,
Read.
3, 2.
read chapters 1 and 2.
Yeah.
See them? Think about them. We'll dive. So chapter 2, remember, is like just some of the elements from last year's number theory course, mainly the notion of induction, integer division with remainder, and some stuff about the definition of the prime number, factorizations and stuff. Tomorrow will be very practical as well. We'll tackle some of these problems here in the reading notes and dive in and integrate some things. Okay. So have a quick read through chapters 1 and 2. Any questions or any queries you have, any clarification you want, we can discuss that tomorrow as well. And we'll do lots more work as well. Okay. Okay.